Okay, today we are finally moving on from stoichiometry and limiting reactants, and we are going to start talking about solutions. So the first thing I want to do is just go ahead and define what even is a solution. It is a homogeneous mixture of a solid dissolved in water. So fancy way of saying you dumped some solid stuff into water and it dissolved. If you've ever heard the term electrolyte before, that is a fancy term for when a salt dissolves in water. So if you are thinking about drinking, I don't know, Gatorade, Propel water, anything like that, because it has electrolytes in it, it has salts in it, not just sodium chloride, but other salts as well. The first thing you have to understand about solutions is that like dissolves like. And that's something you may or may not have heard before, but basically some things, some molecules will dissolve in water and others will not. Water is a polar molecule, as you should already know when we went over how to determine if a molecule was polar and we were using that VSEPR chart. But water is polar, so that means that water can dissolve other polar substances. Water cannot dissolve non-polar substances, which is why when you try to mix oils with water, it doesn't work because oil is non-polar and water is polar. Therefore, a polar substance cannot dissolve a non-polar one. Polar substances can only dissolve other polar substances, hence the saying like dissolves like. So here's a diagram of what happens when water and a polar substance are mixed and when water and a non-polar substance are mixed. So over here on the left-hand side, where it says hydrophilic, these little green and gray things are polar substances. So on this end, the green end of that polar substance is probably going to be a negative end, and on the gray end of that polar substance is going to be a positive end. So we have that positive, that negative happening. And on the water molecule itself, which are these right here, we know what this is. This is H2O. This is a terrible color that I'm writing in, actually. Let me change that real quick. Better. We have H2O over here. And we know that the hydrogens are positive and the oxygens are more negative because of that unit where we discovered polarity and what it means. So what's happening is the negative end of the oxygen is attracted to the positive end of the polar substance, and that's going to yank that positive thing off. So the little gray dot's going to float around over here. And then the positive hydrogens are going to be, whoops, too far. The positive hydrogens are going to be attracted to the negative end of that polar substance, and it's going to yank that apart. And so slowly this polar substance will dissolve. Well, the issue over here with hydrophobic things or non-polar substances is that those positives are all over the molecule. There's no negative end for there's no negative end for the hydrogens to be attracted to. So water can't pull that molecule apart because there's no difference in charge that would allow it to do so. So that's why non-polar substances do not dissolve in water. So solubility is the next term to discuss. And solubility is really how much of a solute, that's the thing that is going to dissolve. So if you were going to throw some salt into water, salt would be the solute. So we want to know how much of that solid thing will dissolve in the solvent. Most of the time in a solution, your solvent is water because water is the best at dissolving things on the whole. So 9 times out of 10, your solvent is water. Your liquid part is water. Your solute or your solid part will vary greatly. Okay, and we say that something is soluble. Whatever solid thing you're trying to dissolve is soluble if 0.1 moles of that thing will dissolve in 1 liter of a solvent or of water. So If you take 0.1 moles of some solid and then put that into 1 liter of water and it dissolves, then we say that thing is soluble. If it does not dissolve in 1 liter of water, then we say that thing is insoluble, or it will not dissolve in solution. So if we think about that for a second, 1 liter of water is a lot if we're only talking about 0.1 moles of a substance. So if we take a tiny little bit of a substance and throw it in a crap ton of water and it doesn't dissolve, it's very likely that that thing cannot dissolve in water. And it doesn't matter how much more water you add, it's never going to dissolve. So that's why we say it's soluble if this much will dissolve in that much water. There are a few things that will affect the solubility of certain solids, of certain solutes. One is the nature of that solute. So is it soluble in the first place? i.e. will 0.1 moles of it dissolve in 1 liter of water? The second thing is agitation. So if you just dumped a bunch of salt into a glass of water, it's not going to dissolve right away. It's going to sit on the bottom for a while. But if you stir it up, it dissolves much faster. So that's what agitation means. Stirring or shaking of that solution will cause the solute to dissolve faster. Temperature can help the solubility of substances. So if a solute is put in water and that water is cold, it's harder for that substance to dissolve than if that water was really, really hot. And the reason for that is mostly because of molecular movement. That movement of those molecules causes them to travel around faster and interact with more of the solid substance than they would have if the water was colder. So that movement can trigger the dissolving action faster. And then the last one, actually, before I move on to the last one, I do want to note that for a gas, for gaseous substances, the solubility is actually going to decrease as the temperature increases. And I'm not going to talk about why that is right now. We'll talk about that more when we get to the gases unit. But just know that for a gas, that's actually the opposite. And then the last thing that can affect solubility is the surface area of a solid. So think of it like this. If you have sugar, like just a little packet of sugar, and you dump that in water, that'll dissolve fairly quickly. But if you have a sugar cube and you drop that into water, it's going to sit there for quite a while. It's going to take a long time for it to dissolve, even if it's the same exact amount of sugar. Because in the sugar cube, there's less surface area of the solid that's exposed to the water. So it has to dissolve slower than the powder, because the powder is more spread out and water can interact with more surface area of that solid and dissolve it faster. Here is a table that's very important. This is a solubility rules table. How you read it is this. On the left are certain ions. You will recognize some of them. Some of them you might have to look at your polyatomic ion chart to recognize, but still, nitrates, acetates, those halogen ions, sulfates, carbonates, phosphates, hydroxides, sulfides, the metal ions, and ammonium. So all of these ions are listed on the left. And then on the right is their solubility trend. So if you have something that contains a nitrate, so if it was potassium nitrate or magnesium nitrate or whatever, that thing is going to be soluble in water. So if you toss that into water, it would dissolve. If you had something bonded to an acetate, it's going to be soluble unless that thing happens to be silver acetate, in which case it's only going to be moderately soluble. Like, it'll dissolve-ish. If you're dealing with a halogen, a chloride, a bromide, an iodide, those are all going to be soluble unless they happen to be bonded to silver, lead, or mercury. This one says lead chloride is slightly soluble in cold water and moderately soluble in hot water. So this is telling you a trend and its exceptions. So if it's any chloride, bromide, or iodide, it's going to dissolve unless that thing happens to be silver chloride or silver iodide, or maybe, I don't know, mercuric chloride, or one of those would not dissolve. But other than that, all your chlorides, bromides, iodides are going to dissolve. All your sulfates are going to dissolve, except if that sulfate is bonded to barium, lead, calcium, or strontium. All your carbonates and your phosphates are not going to dissolve unless they happen to be bonded to sodium, potassium, or ammonium. All your hydroxides are not going to dissolve, except if it is sodium hydroxide or potassium hydroxide, and then barium and calcium hydroxide are soluble-ish. All your sulfides are not going to be soluble, except if it's bonded to sodium, potassium, ammonium, and alkaline earth metals. Okay, so this table is not that hard to read. You just have to read it. Don't skim it, read it, so that you don't read it incorrectly. Next is types of solutions. There could be a solution that is unsaturated, which means it contains less solute than the solvent has the capacity to dissolve at a specific temperature. So my best example for this is if you had an entire glass of water and you put 1 teaspoon of salt into it. You could absolutely put more salt into that glass of salt water and have that salt dissolve. However, if you had that same glass of water and you put like a whole cup of salt into it, yeah, you might be able to dissolve that salt in the water, but no more is going to dissolve into it. That's a saturated solution. It has the maximum amount of solid in it that will dissolve in that given amount of liquid. And then last but not least, we have a supersaturated solution, which is way more than that liquid could conceivably dissolve. So say you have that same glass of water and you're trying to put like 2 entire cups of salt into it. At some point, that salt is going to stop dissolving because there's no more that can dissolve in the available liquid. Okay, so unsaturated, more can dissolve. Saturated, no more can dissolve. Supersaturated, you already have more than can dissolve in that amount of liquid. Here is a solubility curve, which you are going to have to use in this class. So let me just give you a quick idea of what a solubility curve is. Down at the bottom here, we have temperature in degrees Celsius. It's not always in degrees Celsius, but a lot of the time it will be. So we have a range from 0 degrees Celsius to just over 100 degrees Celsius. And then on the left, this axis right here, the y-axis, we have solubility, grams of solute per 100 grams of water, okay? So once again, solute means the solid thing. So grams of solid in 100 grams of water, okay? So if we read this here, let's take this first point right there. For KNO3, which is the subject of the solubility curve, at 0 degrees Celsius, let's see, what is that, like 11? We'll say 11 grams of KNO3 can dissolve in 100 grams of water. At 10 degrees Celsius, 23-ish grams of KNO3 can dissolve in 100 grams of water. At 60 degrees Celsius, if we trace this line up, 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 up until we reach the green line, 113-ish grams of KNO3 can dissolve in 100 grams of water. So what this green line really represents is a saturation line. Where the green line touches, that solution, that 100 grams of water, is saturated by KNO3. Anything below that line, anything over here in this region, that's unsaturated. It means that more could dissolve. Anything over that line in this region is not all going to dissolve. So if you, like let's say at 10 degrees Celsius, you tried to dump 70 grams of KNO3 in 100 grams of water, it's not going to dissolve. You have supersaturated that solution. But if you increase the temperature to say 80 degrees, that 70 grams could dissolve in 100 grams of water. So that's how you're going to read this solubility curve. And there will be a practice worksheet to show you how that works. Okay. Here's a nice visual representation of a saturated solution, an unsaturated solution, and a supersaturated solution. So in unsaturated solutions, you're not going to see any solid at the bottom. In a saturated solution, you might see like the tiniest hint of a solid at the bottom, but in a supersaturated solution, you're going to see a bunch of solid start collecting at the bottom of whatever it is you're trying to dissolve it in. Okay, so sample questions to work on right now. Number 1 says, for which substance is solubility least affected by the changes in temperature? So what I want you to do with these is pause this video and try to answer these on your own before I go over the answer, if you think you can do that. If you are looking at this graph over here and going, man, I have no freaking idea how to do any of this, then you may want to follow along. But if you think you can, go ahead and pause it and try and answer these questions before I give out the answers. Anyway, so for which substance is solubility least affected by change in temperature? Well, if you look at this, what you're looking for is the most horizontal line, because the most horizontal line means that the solubility is changing not by a lot. So the one, just taking a quick glance at this, the one that I see that changes the least is sodium chloride, because if we look at that line going across, sodium chloride at 0 degrees Celsius, just under 40 grams can dissolve. Sodium chloride at 100 degrees Celsius, right around 40 grams can dissolve. So that solubility did not change, so by a lot anyway. So my answer would be sodium chloride is least affected by changing in temperature. The next one is, name a substance that shows a decrease in solubility with increasing temperature. So for this, you're looking for a line with a downward slope. I see 2 of those looking at this graph at first glance. If somebody else sees another one, please let me know. But the first one that's very, very, very obvious is NH3 or ammonia. That one kind of goes down pretty sharply. So you could say ammonia for that. The other one is a little bit less obvious down here, but cesium sulfate is the other one, CeSO4 3. This one asks for which substance is solubility most affected by the change of temperature. So kind of the opposite of number 1. So you want to look for the steepest upward line, the steepest line. So again, just glancing at this graph really quickly, I would say KNO3, because it starts all the way down here at around 15 and goes off the chart before you hit 100 degrees Celsius. So I would say KNO3 would be most effective. This one asks, what concentration of KCl is at 50 degrees Celsius? So you find KCl, which is right here. Actually, I'm going to do that in a different color. Find it. Let me highlight that line really quickly. And then we go to 50 degrees Celsius and we trace up until we find that point. And that looks like it's just above 40. So I'm going to say 41 grams per 100 grams of H2O is the solubility of KCl at 50 degrees Celsius. And then the last one says, at what temperature does the solubility of KNO3 begin to exceed that of NaNO3? So now we have to find KNO3 and NaNO3. And we want to know at what point does the solubility of this one exceed this one. So at what point is the line of this one higher? Well, here's where they meet. So just above, I'm going to say 135-ish, but that's not what the question asks. It asks temperature. So we want to trace that down, down, all the way to the bottom. And just guesstimating, we're at about here where the KNO3 starts to go above NaNO3. So I'm going to say about 72 to 73 degrees Celsius is that temperature when KNO3 exceeds NaNO3. So hopefully reading this graph was not too terrible for you. If you need help reading graphs, please talk to me, because reading graphs is a really, really valuable skill to have. So I'm hoping that most of you have that. If you need help, again, please ask me. We're going to be doing a lab this week in class and practicing how to read solubility curves, how to use the solubility rules, etc., before we get into solutions calculation.